Today's video is looking at the absorption and emission spectra of elements and how they provide evidence that electrons are arranged in distinct energy levels, like we've discussed in past videos. It can also be used to identify some elements in matter. So if we have a look here, we've got a bit of a review of the Bohr model of the atom. So in the Bohr model, he stated that the protons and neutrons were in our nucleus in the center, and the electrons could be found in distinctive energy shells surrounding that nucleus. Electrons can only exist at certain energy levels with a discrete amount of energy. What was noticed was that electrons can transition between energy levels. So if we have a look at these different energy levels here, we've got n equals 1, 2, 3, 4, 5 and 6. And so what happens as electrons are transitioning between these levels here, we notice that it gives rise to a different absorption and emission spectra. If an electron absorbs a discrete amount of energy, it can then transition to a higher level, and this is classed as its excited state. So it could go from n equals 1 to 2, that's classed as excited. If an electron emits a discrete amount of energy, then it can transition to a lower energy level. So it might go from n equals 3 down to an n equals 2. Here we have an absorption spectra. If we look at these arrows here on the diagram, they are showing electrons from, in this case here, the n equals 2 and transitioning to the n equals 3 energy level. Here the energy n equals 2 is going to the n equals 4 and then the 5 and the n equals 6. On the right hand side of the diagram over here, we have an absorption spectrum. This absorption spectrum here shows some black lines on the coloured background. Below here, it shows the energy levels of the atoms from n equals 1, ground state, n equals 2, 3, 4, 5 and 6. The coloured arrows here correspond to the colours that are missing on the spectrum above. So if we've got here our arrow that is going from n equals 2 to 3, our red arrow, that electron has transitioned up an electron shell. The energy that's absorbed corresponds to the wavelength of red light. If we look at our blue arrow here, you can see that the n equals 2 has gone to n equals 4. And so on. From here we've gone the n equals 2 to n equals 5. This energy, electron's energy absorbed, corresponds to the black line that is on the wavelength of blue light. To summarize this, the electron transitions between n equals 2 to 3, 4, etc. The electrons absorb the energy, and then the energy that's absorbed corresponds to the wavelength of visible light. Now the arrows, if you have a look here at the Bohr model, the arrows are going in the opposite direction. Now electrons are going from higher energy levels to a lower energy level. Again, each electron transition has its own colour. On the right hand side here, we can see an emission spectrum. This one here shows colour lines on a black background. The energy levels are from n equals 1, ground state, right through to n equals 6. Here we have a look at our red arrow. So on the left hand side we can see our red arrow, and also over here on the right hand side. So our red arrow is when an electron transitions from a higher n equals 3 to a lower level n equals 2. It's emitting a discrete amount of energy, and that energy corresponds to the wavelength of red light, which we see on the spectrum above. And the same sort of thing you can see here from purple. If you have the electron transitioning from n equals 6 down to n equals 2, well, that amount of energy corresponds to this purple section here on the emission spectrum. So to summarize this one, the reason for the coloured lines on the black background this time is that they correspond to the energy that's emitted when an electron transitions from a higher energy level to a lower energy level. So not all transitions correspond to wavelengths that we can actually see. If we have a look here, we've got our hydrogen emission spectrum. the diagrams for it. We can see that we have different types of electromagnetic radiation emitted when electrons are transferred from higher to lower energy levels. We have UV radiation, visible radiation or visible light, and infrared radiation. UV radiation corresponds to transitions from the n equals 1 or ground state. At this case, we have the highest energy, high frequency, but short wavelength. The visible light, that corresponds to the transitions to the n equals 2 level. This one here is where we have violet is the highest energy and red is our lowest energy. Finally, electron transitions to the n equals 3, well, they correspond to the infrared radiation. They have the lowest energy, low frequency, but the longest wavelength. If we have a look on some further spectrums here, we have hydrogen, sodium, helium, neon, and mercury. You can see that each of these lines are corresponding to different wavelengths, and this is how we can tell that this one here is hydrogen, whereas this one here is helium, because those different energy transitions that have occurred with the electrons moving from shells corresponds exactly to that element. Here we have some atomic spectra of our noble gases. And on the last one here, we've probably in junior school done some flame tests. When you burn different metals in a flame, you end up with different lights, colours that you can see. Here we have lithium, the actual flame spectrum for lithium, but here is what we actually see, colours of various gases that you can see as well. Well, thanks for watching and see you next time.